Let's say we have a rubber chicken, and we're bored during quarantine, so we want to balance this chicken on one finger. How do we determine the exact location that we place this chicken so that it will balance perfectly on our hand? The center of mass is a unique point on every object that, if you add the weighted relative position of every single small piece of mass on this object, it would sum up to zero. An interesting property about the center of mass is that if you exert a force on that one point, it will not cause the object to rotate. Or another way to say it is the center of mass is the balance point of your object. So how do we calculate the exact position of the center of mass? Well, let's first divide the chicken into infinitely thin pieces, and then place the sliced chicken on a x-axis where 0 is at the very left and positive x is pointing to the right. Now let's take a infinitely thin piece of chicken, and we want to find the mass of this thin piece. So if we say that the total mass of this chicken is m, then the mass of this small piece must be dm. We said before that the location of center of mass is basically the weighted average of the position of all masses on an object. So quick sanity check. If we add up all of the small pieces of mass, or dm, multiplied by its distance relative to the feet of the chicken and then divided by the total mass, the units of dm is kilograms, of x is meters, and that's divided by m in kilograms again, so that leaves us with a unit of meters, which is what we want. Now back to the chicken. Let's approximate it as having a uniform mass density with respect to x. So what that means is the mass of the chicken is evenly distributed from left to right. And since we know the total mass of the chicken is m and the total length is l, then the mass density, lambda, is m over l. Since we now know the mass density, we can calculate the mass, lowercase m, of a thin piece of chicken. So that would be equal to dm, or lambda times dx, where dx is the width of your very thin piece of chicken. Now that we know dm, we can simply plug it into the equation for location of center of mass and solve. So what we get is the integral of dm times x, which is the location of that piece of mass over the total mass of the chicken. It's also equal to the integral of lambda dx times x over m, where we just plugged in the value of dm that we solved above. And we're integrating this from 0 to L, since we are adding up all the small masses from the toe of the chicken all the way to its head. Then the answer that we get is 1/2 L, so the position of center of mass is exactly at half the length of the chicken. And this makes sense. If we're saying the chicken is of uniform density with respect to x, then we're basically approximating it by a block. And the center of mass of a block of uniform density is just at the very center. Okay, so now what if we have a piece of cheese? And this time, instead of having uniform mass per unit length, it has uniform mass per unit area. So this time we have to treat the block of cheese as a two-dimensional object, and we have to calculate the location of center of mass in the x and y direction separately. Let's calculate the position in the x direction first. I want to integrate thin vertical slices of cheese, and by the law of similar triangles, we know that for each triangle, x has a special relationship to y. By the law of similar triangles, y over x is always equal to h over l, where h is the total height of the cheese and l is the total length of the cheese. So we can rewrite that into y is equal to h over l times x, and the total mass of the cheese is m. The total mass must be equal to rho times the total area, which is equal to half of L times h. Then rho is equal to m over 1/2 L times h, or 2m over LH. Then a thin piece of mass, or your differential piece of mass, must be equal to rho times dA, where d is equal to y times dx. And that is basically because you're integrating tiny rectangles of height y and width dx. But we can't integrate y with respect to x, so let's plug in y equals h over l times x, the equation that we got earlier. dm is then equal to rho times h over l times x dx. Now we can plug that into the formula for location of center of mass again, and we are integrating with respect to x, so it's from 0 to L. And the answer we get is 2/3 L, so the center of mass in the x direction is at 2/3 the length of the cheese. Now finally, let's solve for the position in the y direction. So we can use the same relation between y and x that we found before, except this time we're trying to plug in x in terms of y, so we flip the equation. This time we're integrating horizontal slices, so from down to up, which means that at y equals 0, the total length of the cheese is equal to L, and as y equals to h, the total length goes to 0. This time, the area of the rectangles that you're integrating is equal to L minus x times dy, where L minus x is the length of the rectangle and dy is how tall it is. So if you plug all that in back to the formula for center of mass, you get an answer of 1/3 h. So the center of mass in the y direction is at 1/3 the height of the piece of cheese. With these calculations, you'll know exactly where the piece of cheese balances, if you were a mouse.